Hey, welcome back to Circles and Geometry. I know that you missed it, right? So our first section, Circles and Circumference, is where we talked about radius, diameter, chords. Remember that a diameter is a special type of chord. So it's a special type. Radius can never be a chord because a chord has both endpoints on the circle. And we know that a radius has one endpoint at the center and one on the circle. So radius, not a chord. All right, second section, angles and arcs. We had a couple of different types of arcs. Minor was less than 180. Major, greater than 180. Semicircle, exactly 180. And these are all in terms of degrees. Naming minor arcs, use only the endpoints and put the arc symbol. Naming major arcs, use 3 letters and put the arc. Semicircle, it really doesn't matter because it's 180 degrees either way. Central angles is any angle that has a vertex at the center. And we also know that central angles are equal to the arc that they form. Section 3, arcs and chords. Inscribed, remember that that means every vertex is on the shape. So whatever is on the outside shape, so if it were a circle perhaps, and I'm just going to draw it freehand so it's probably going to look terrible. Oh, it's not that bad. If it was a circle with a triangle, this triangle would be considered inscribed because it has a vertex, or every vertex is on the circle, where circumscribed is the shape on the outside, so the circle would be circumscribed. Then we have our section 4, inscribed angles, and we have intercepted arcs. So if we have a circle, okay, now that is not a circle, but you know, anyway. If we have a circle and we have an arc formed by endpoints of an angle, so if this was angle ACB, it forms AB, which means AB is our intercepted arc. All right, onward. Moving into section 5, tangents. Now, I know that you remember this from our SOHCAHTOA days, right? Honestly, I don't know why we use tangent there and we use tangent here when they are two completely different things. So I'm going to look that up and I will tell you when I see you, okay? So tangent, any line that touches a circle at exactly one point, and then naturally the point of tangency would be where it touches that line. I mean, surprising, right? So check this out. Here's circle A, and we have point B. So this is our point of tangency, and then line L would be our tangent. Pretty easy, right? So if we could just keep moving that around anywhere, so it's any line that touches it exactly one time. Now you'll notice that it can't go through the circle, because if it did, something like this, it would touch it twice. Okay? So any line touches a circle once. All right, our first theorem for this, if a line is tangent to a circle, then its point of tangency is perpendicular to the radius or diameter. So if we know that this line, let's call it M, is tangent, and this would be our point of tangency, and if we know that this is a diameter, that automatically means that this is a 90-degree angle. Ta-da! Pretty cool, right? And it could work for it only being a radius also, if I could shrink that down and just make it a radius, still perpendicular to the point of tangency, always, no matter what. All right? So we're going to use that and use the Pythagorean theorem. Oh my gosh! I know you're surprised, right? Pythagorean theorem, geometry, oh my god. All right, so find the diameter of circle Q. Remember that this is how you denote circle. It's the abbreviation. If RS, right here, is tangent to circle Q at point R. So if we know that this is tangent, well, then we also know that this makes a right angle, right? Okay. Then we're given that QS is 20, so we're talking about from here to here, which would be our hypotenuse of our right triangle, and our S is 16. So from here to here is 16. So we have a squared plus b squared equals c squared. Remember, c is always the hypotenuse, so this is your c. A and b are interchangeable. It doesn't matter where you put them. So we do 16 squared plus x squared, a squared, b squared, it doesn't matter, equals 20 squared. Simplify that first. 20 squared is 400, so this equals 400, and 16 squared is 256. Subtract our 256 from both sides, and we end up with a squared is equal to 144. Take the square root of both sides because square root and square are opposites, and we end up with a is 12. So our missing side, QR, is 12. But come back to this question. Look, it said find the diameter. Oh my gosh. Well, check this out. We have from Q to R is 12. Well, guess what? That's the radius. And we need the diameter. OMG. Maybe we should just double it. Oh my god. So the diameter is 24. Woo! I know. So excited. And onward. Now check this out. The converse is true too. What? So remember, it's if a line is tangent to a circle, then its point of tangency is perpendicular to the radius or diameter. And what does converse mean? Converse means flip it. So we flip it. If a radius or diameter is perpendicular to a line, then it is a tangent line, or you can just call it a tangent. Now you'll also notice that I rewrote this to make sense. I didn't just put if it's a point of tangency is perpendicular to radius diameter. It doesn't make any sense. Okay, so we had to make it make some sense. So if it is, or if a radius or diameter is perpendicular, then it's a tangent line. All right, one more theorem for this section anyway. All right, don't talk about my evil laugh. I didn't practice. If two segments come from the same exterior point and are tangent to a circle, then they are congruent. Now the reason I put the ice cream cone here is because this is kind of what it reminds me of. If I were to make the top portion of the circle, oh no, that's terrible news. I don't like that. If I were to make the top portion of the ice cream cone just perfectly round, like this, and then let's say I wanted to connect my cone to my ice cream, then I would do something like this. And, well, any good cone maker and any good ice cream scooper would want it to be nice and even on both sides. So we get congruent tangent lines. So same exterior point, tangent to the circle, and you have an ice cream cone. All right, now wait, are you ready for this one? Okay, so here we have tangent here and tangent to here. So these are two tangent lines. Okay, so two tangents. All right, now we know that these are congruent, correct? Okay, well, we also know that the radius is a line that starts at the center and goes to the circle, right? So it goes touches the circle anywhere. Well, we could draw a radius there, right? And we could also draw one right, okay, wait for it, right there. And you know what, I'm going to draw that in a different color so I can kind of show you something here. Okay, so let's do that. Okay, so now you're thinking, oh my gosh, what's happening? Well, here's what we know. We know that these are congruent because they are both radii. Yes, that's plural for radius. Okay, so now you're looking at this and thinking, oh my gosh, what is happening? Well, radius to the point of tangency is a right angle, and same with over here. And then watch what else we can do. Oh my gosh, get ready for your mind to be blown. Da 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 da. We have two congruent right triangles. Two congruent right triangles. What? Yeah, check that out. For real. Not to mention, this is also a kite. Remember when we talked about kites and we had two sets of congruent sides and they were adjacent to each other? They were consecutive sides. Look at that. Oh my gosh. It's amazing, right? And if we went even further with the idea of the kite and we connected these points from here to here, then we would also have more right triangles. We would have one right here, right here, right here, right here, and then we have these two congruent to one another, and then these two out here congruent to one another. So then we would have four congruent right triangles, and oh my gosh, your mind is officially blown, right? I know. I can't believe it myself. It is so shocking. Just shocking. All right, well, I don't know if you've seen the video where, can't even remember what it's called, but at one point the guy says, well, about that time, eh, chap? And another guy says, Rotto.
Now this is a story all about how my life got turned upside down, and I'd like to take a minute, just sit right there. I'll tell you how I became the prince of a town called Bel Air.
I hope you're jamming like that baby on the boombox. Check him out in his roller skates. Rockin'.